Welcome to the deep dive. We're digging into a set of sources you've given us, basically our roadmap for today.
That's right.
And our topic is reinforcement learning for AI agents. It's really about this core question. How does an AI agent learn to make, a sequence of decisions? How does it learn to act to reach a goal?
Yeah, it's not just about prediction based on data we feed it. It's about action in a complex world.
And this is fundamentally different from, say, supervised learning.
Absolutely. Reinforcement learning, or RL, is really about learning by doing, learning from the consequences of actions, trial and error.
Okay. Sounds fascinating. So we're going to look at its roots, the core ideas, the math.
The algorithms, definitely, and some pretty amazing applications, too.
All right, let's dive in. Where do we start? The surprising origins.
Yeah, let's start there, because, you think AI, you think computers, right? But the real bedrock ideas for RL, they come from psychology, behavioral psychology, actually.
Really, like experiments with animals and stuff?
Exactly that. People like Pavlov, B.F. Skinner, Thorndike, they were studying how we learn.
Okay, so conditioning, rewards, punishments.
Precisely. Thorndike's law of effect behaviors followed by good outcomes get repeated. Skinner's operant conditioning shaping behavior with rewards and penalties. These concepts, they're basically the blueprint for RL. It's learning through feedback.
Huh. So it's not just abstract theory, it's inspired by actual learning processes.
It really is.
Yeah.
And understanding that helps make sense of why RL works the way it does. It provides that intuition.
So how does this translate into the digital world? What are the components? You mentioned this RL loop.
Right, the core interaction. Think of it this way. You have the agent, that's the learner, the decision maker.
The AI itself.
Yes. And then there's the environment. Everything outside the agent it interacts with. Its world, so to speak.
Okay.
The agent perceives the environment through a state. Yes, that's its snapshot of the current situation. What it needs to know to make a decision.
And based on that state, it chooses an action. A.
Exactly. It picks an action from its available options. And that action affects the environment.
Changes things.
Right. The environment then transitions to a new state. And this is key. It gives the agent a reward.
Feedback. Good job, bad job.
Kind of. It's a numerical signal. Could be positive, could be negative, could be zero. It tells the agent how good that action was in that particular state.
And this just repeats. Observe state, take action, get new state, and reward.
That's the loop. Over and over. That's how the agent gathers experience.
Okay, so it's gathering experience, getting rewards. But what's the ultimate goal? Just getting the biggest reward right now?
Ah, good question. And no, not quite. That's where it gets really interesting. The real goal is to learn a policy.
A policy, like it's strategy. It's rules for acting.
Exactly. A mapping from states to actions. What should I do when I'm in this situation? And the objective isn't just maximizing the immediate reward, it's maximizing the cumulative reward.
Cumulative, so the total reward over time.
Yes. The sum of all the rewards it expects to get, potentially far into the future.
That sounds much harder. It means thinking ahead, right? Like in chess, you might sacrifice a pawn now for a better position later.
Absolutely crucial. That's foresight. Good long-term outcomes often require taking actions that don't pay off immediately. Maybe even seem bad in the short term.
So how does it balance immediate versus future rewards?
Mathematically, that's often handled with a discount factor, usually called gamma, a number between 0 and 1.
And that discounts future rewards, makes them less valuable.
It can, yes. If gamma is close to 1, the future is almost as important as the present. Very long-term thinking. If it's closer to 0, the agent becomes more focused on immediate gratification. It also helps keep the maths tidy for problems that might go on forever.
Right. And there's this idea, Sutton's reward hypothesis.
Yeah, Richard Sutton, one of the pioneers. His hypothesis is powerful. Basically, any goal or purpose can be framed as maximizing the expected cumulative reward, just maximizing one number.
Wow, that's a big claim. If that's true, RL could be a universal framework for intelligent goal seeking.
It's a very influential idea, certainly.
Okay, so if we want to describe this whole setup, formally, agent, environment, states, actions, rewards, thinking ahead, what's the mathematical language for that?
That brings us to the Markov Decision Process, or MDP. It's the standard mathematical framework for formalizing these kinds of sequential decision problems where there's uncertainty.
MDP, got it. What are its key parts?
Well, it uses the things we just talked about. A set of states, S, a set of actions, A, available in those states. Then, crucially, transition probabilities, PSS.
Okay, that's the probability of ending up in states prime if you take action A in states S.
Exactly. It captures the dynamics of the environment, how actions lead to new states. Then there's the reward function, RS, which tells you the expected reward. And finally, our friend, the discount factor.
And the Markov part, why is that important?
The Markov property. This is a critical assumption. It basically says that the future depends only on the present state in action, not the entire history of how you got there.
So the current state tells you everything you need to know to make the best decision moving forward. You don't need to remember everything that happened before.
Precisely. It simplifies the problem enormously. Otherwise, the agent would need an impossibly long memory. The current state summarizes the relevant past.
Okay, so the MDP defines the problem space. How does the agent actually learn the best policy within that space? How does it know what's good?
That's where value functions come in. They're absolutely fundamental. Value functions quantify how good it is for the agent to be in a certain state or to take a certain action in a state.
Good in terms of future rewards.
Exactly. In terms of expected cumulative future reward, long-term value.
Okay.
There are two main types. The state value function, DCS, is the expected total discounted reward starting from state ANGs and then following a particular policy.
How good is the state overall if I stick to my current strategy?
Right, and then there's the action value function, QSAA. That's the expected total discounted reward if you take action A in state ANGs and then follow your policy thereafter.
How good is it to take this specific action right now?
Yes, and the Q function, QSA, is often really useful because if you know the optimal Q values, choosing the best action is easy. Just pick the action A that has the highest Q value in your current state A's.
Makes sense. But how does the agent learn these V or Q values? They depend on future states and rewards it hasn't even experienced yet.
That's the magic of the Bellman equations, named after Richard Bellman. These are recursive equations. They define a value function in terms of itself.
Recursive? How?
They express the value of a state, like VS, based on the immediate rewards you can get, plus the discounted values of the next possible states you might land in. Or for Q, it's the immediate reward plus the discounted value of the next state after taking action A.
So the value right now depends on the value later on. It connects the present to the future.
Precisely. It's like saying the best path from here involves taking the best path for the next step onwards. This relationship is the core of how many RL algorithms work. They iteratively update the value estimates using these Bellman equations, propagating information about future rewards backward in time. It's sometimes called bootstrapping or backups.
And there are optimal versions of these equations.
Yes, the Bellman optimality equations define the maximum possible value functions, VSS and Qs. Finding these optimal values is equivalent to finding the optimal policy.
Okay, that's a lot of the theoretical underpinning. Psychology, the loop, MDPs, value functions, Bellman equations. Now let's get practical. How do AI agents actually use this? What are the main algorithmic approaches?
Right. This is where the rubber meets the road. The choice of algorithm often depends on the problem, especially the nature of the action space. Can the agent choose from a few distinct options or a whole continuous range?
Okay, what's the first family?
Let's start with value-based methods. The classic example here is Q-learning. The name kind of gives it away. Its goal is to directly learn that optimal action value function, QMR.
So it tries to figure out the long-term value, the quality of taking each possible action in each possible state.
Exactly that. It builds up a table or function approximating QS. Once that's a good estimate, the policy is simple. In any state O's, just choose the action A with the highest Q value.
And Q-learning is important because...
So a couple of key properties. It's model-free. It doesn't need to learn a model of the environment's transitions or rewards. It learns directly from the state, action, reward, next state experiences it gathers.
That sounds very useful for complex, unknown environments.
Hugely useful. And it's also off-policy. This means it can learn the optimal policy, Q, even while it's exploring and trying out different actions that might not be part of the current best guess of the optimal policy. It learns about the best way while behaving, perhaps, suboptimally for exploration purposes.
Okay, so practical, learns directly, can explore. What kind of problems is Q-learning good for?
It really shines in problems with discrete action spaces. Think navigating a grid world, up, down, left, right, choosing moves in simple board games, or controlling systems with a finite number of settings.
But what if the actions aren't discrete? What if the agent needs to control, say, the precise angle of a robot arm or the speed of a car? That's a continuous range.
Exactly.
Yeah.
Q-learning struggles there. You
Wow.
can't really build a table for an infinite number of actions. That's where policy-based methods come in.
So these learn the policy directly.
Yes. Instead of learning value functions and then deriving a policy, these methods directly parameterize the policy itself, say, as a neural network that takes the state as input and outputs the action, or probabilities over actions. Then they adjust the parameters of this policy network to maximize the expected cumulative reward.
Ah, so it's directly learning the strategy.
Right. Methods like policy gradients are powerful for continuous action spaces, which you see all the time in robotics and control. They can also naturally learn stochastic policies.
Meaning the policy outputs probabilities for different actions rather than always picking one.
Correct. Which can be really useful for exploration or in situations where being unpredictable is actually good.
Okay, value-based for discrete, policy-based for continuous. Is there anything that combines them?
There is. That's the third major family. Hybrid methods, most famously actor-critic methods.
Actor-Critic sounds like a performance review.
Kind of. You have two components, often two neural networks. The actor is the policy it decides which action to take, just like in policy-based methods.
Okay, and the critic?
The critic learns a value function, often the state value function VS, or the action value function QSA. Its job is to evaluate the actions taken by the actor.
So the critic tells the actor how well it's doing.
Essentially, yes. The critic provides feedback like, that action you took in that state led to a better than expected outcome, or worse than expected. This feedback signal helps the actor update his policy more effectively.
Why combine them? What's the advantage?
Actor-critic methods often strike a good balance. They can handle continuous actions like policy-based methods, but the critic's value estimates can reduce the variance and improve the stability and sample efficiency compared to pure policy gradient methods. They're very popular and effective for many complex tasks.
Right, so different approaches for different needs. Now, regardless of the algorithm, there are some fundamental challenges or concepts in RL, right? You mentioned exploration.
Absolutely. The exploration versus exploitation trade-off is maybe the fundamental dilemma in RL.
Trying new things versus sticking with what works.
Exactly. Exploration means trying actions you haven't tried much before, or actions that don't currently seem optimal, just to see what happens. You might discover a better path. Exploitation means using your current knowledge, picking the action that currently looks best based on past experience to maximize immediate reward.
And you need both. Too much exploration, you never benefit from what you learned. Too much exploitation, you might get stuck in a rut, missing out on something much better.
You've got it. Finding that balance is crucial for learning truly optimal behavior. Simple strategies exist, like epsilon greedy, where most of the time you exploit, but with a small probability, epsilon, you just pick a random action to explore.
Makes sense. What else is critical?
Well, understanding the difference between deterministic and stochastic policies is important.
We touched on that. Deterministic always picks the same action for a state.
Right. While a stochastic policy outputs probabilities over actions, it might choose action A 70% of the time and action B 30% of the time in a given state.
And stochastic isn't just for exploration.
Not necessarily. Sometimes, in environments with uncertainty or hidden information, a stochastic policy can actually be the truly optimal one, or it can make an agent less predictable. Policy-based and actor-critic methods can learn these naturally.
Okay. And maybe just quickly revisit model-based versus model-free.
Sure. Model-based RL is when the agent explicitly learns a model of the environment. It tries to predict the transition probabilities, passes A, and the reward function, RSA. It can then use this learned model to simulate or plan ahead.
Like, if I do this, the model predicts that will happen.
Exactly. Model-free RL, on the other hand, which includes Q-learning, policy gradients, actor-critic learns the value function or policy directly from interaction, from trial and error, without building that explicit predictive model of the world.
And model-free is often more practical for complex AI agents.
Often, yes. Because building an accurate model of a really complex, messy, real-world environment is incredibly hard. Model-free methods bypass that potentially huge challenge, learning directly from experience. They might need more experience sometimes, but they are often easier to apply.
Okay, this framework is incredibly powerful. Where are we seeing AI agents using RL making a real impact today?
Oh, in a lot of areas, and it's growing fast.
Robotics seems like a prime candidate.
Definitely. Teaching robots complex motor skills, things like learning to walk on 2 legs or 4 over difficult terrain. Think Boston Dynamics. or learning really dexterous manipulation, grasping objects, assembling things. OpenAI training a robot hand to solve a Rubik's Cube was a big RL showcase.
And games, of course. That's where we hear about it a lot.
Yes, games are great test beds. Clear rules, clear goals. RL agents have achieved superhuman levels in chess, Go. Remember AlphaGo.
Yeah.
Also complex video games like Atari, Dota 2, StarCraft 2. They learn strategies humans didn't even think of.
Beyond games and robots.
Autonomous systems. Decision-making in self-driving cars, planning routes, navigating traffic, handling unexpected events. Same for autonomous drones.
What about less physical domains, like optimizing systems?
Absolutely. Resource management.
Okay.
Think optimizing energy grids, managing inventory and supply chains, setting dynamic prices for airlines, or ride-sharing based on demand. Agents learning to make sequences of decisions to optimize some overall business goal.
And personalization, like what I see online.
Yes. Recommendation systems can use RL to learn not just what you might like now, but what sequence of recommendations keeps you engaged longest. It's used in optimizing website layouts, deciding on personalized offers in e-commerce, even explored in personalized medicine for treatment strategies.
And I heard it's even involved in training the large language models, the LLMs.
That's a huge one right now. Reinforcement learning from human feedback, RLHF. Humans essentially provide reward signals by rating the LLM's outputs, and RL fine-tunes the model to produce responses that humans prefer: more helpful, honest, harmless.
Wow, okay. And even finance, using LLM sentiment.
Yeah, that's an emerging area. Using insights from LLMs like sentiment analysis as part of the state or reward signal for an RL trading agent. Still very much research, but shows the versatility.
So RL is enabling some really advanced autonomous behavior across the board, but it sounds hard. What are the main bottlenecks or challenges people face when trying to train these agents?
It's definitely not easy. A major one is sample inefficiency. RL agents often need a huge amount of interaction with the environment, millions or billions of steps sometimes, to learn a good policy. Way more data than typical supervised learning.
Just takes a long time and a lot of compute.
Yes. And related to that is the credit assignment problem, especially when rewards are sparse or delayed. If an agent makes 1,000 moves and then wins a game, which of those 1,000 moves were actually crucial for the win?
Yeah, how do you assign credit back in time to the right actions?
Exactly. Figuring out which early actions led to later rewards is really hard. If the reward only comes at the very end, the signal is weak for all the intermediate steps. That's a fundamental challenge.
Wow. Okay, what a deep dive that was. We went from Pavlov's dogs and Skinner boxes.
All the way to the agent environment loop, states, actions, rewards.
The crucial goal of maximizing cumulative reward, needing that foresight.
Formalizing it with MDPs and the Markov property.
Using value functions and those recursive Bellman equations to connect present and future value.
Then the algorithms, value-based like Q-learning, policy-based like policy gradients, and the actor-critic hybrids.
Hitting those key concepts like exploration versus exploitation, stochastic policies, model-free learning.
And seeing the impact in robotics, games, autonomous systems, optimization, personalization, even training LLMs.
It really boils down to this powerful idea. Agents learning how to make sequences of decisions, how to act by interacting with the world and trying to maximize a long-term reward signal through trial and error.
That's the essence of it, learning by experience to achieve goals.
Which brings us back to that reward hypothesis from Sutton. If any goal can potentially be framed as maximizing some cumulative reward signal, well, that leaves us with a pretty profound challenge, doesn't it?
How so?
If we're building these increasingly powerful agents designed to optimize a single number, that reward, how incredibly careful do we need to be in defining what that number actually represents? How do we make sure the reward function truly captures our complex human goals?
That's a critical point. The problem of reward specification or value alignment. How do you design a reward signal that doesn't have unintended consequences?
Exactly, because a powerful agent focused solely on maximizing that number might find clever, unexpected, maybe even harmful ways to achieve a high score that completely misses the spirit of what we actually wanted.
It's the classic alignment problem. Ensuring the agent's learned objective truly aligns with our intended objective. Designing the reward might be the hardest part of RL.
A powerful agent optimizing the wrong thing. That's definitely something to think about.
Indeed. It's not just about making them learn better, but making them learn the right thing.
A crucial thought to end on. Thanks so much for unpacking all of this with us.
My pleasure.
And thank you for joining us on this deep dive. Keep exploring.